Hello, this is Richard White with a brief presentation on computer science versus computer programming, algorithms, and the Fibonacci sequence. Computer science and computer programming are two fields of study, and although they both have to do with computing, there's some important differences between the two. In this video, we're going to explore those differences using a real-life example. Computer science is a field of study that tries to answer the questions, what can we compute? And how can we best compute it? Computer science investigates how one can solve problems, and especially what algorithms one can use to solve problems. An algorithm is a step-by-step strategy that's developed to solve a certain class of problems. The idea is that once you have an algorithm, think of it as a recipe for solving a problem, you can use that algorithm to solve other similar types of problems, even as the size or scale of the problem increases. When considering problems from a computer science perspective, it helps to be able to think logically and to be able to develop abstract models of problems. Some people consider computer science as a type of symbolic puzzle solving. Computer programming, on the other hand, consists of taking an algorithm and coding it in a programming language so that the instructions can actually be executed on a computer. If a computer scientist is concerned with the logic of an algorithm, the computer programmer is concerned with getting the algorithm to actually run on a machine, and it requires knowing the syntax of a specific programming language or languages. This too requires logical thinking. Most computer science classes or computer programming classes include a little bit of both of these studies. A typical introductory class might study the logic of a sorting algorithm, for example, and then a student will write a program using a specific language to demonstrate that sorting process. To demonstrate the difference between computer science and computer programming, let's take a look at this problem. Pause the video and see if you can identify the next number in this sequence. Here's the pattern. After the first two numbers, each following number is calculated as the sum of the previous two numbers. 1 and 1 is 2, then 1 and 2 is 3, then 2 and 3 is 5, and so on. The next number in the sequence is 8 plus 13, or 21. And it goes on up from there. You may already know this sequence from a math class. It's called the Fibonacci Sequence. So maybe we know how the Fibonacci sequence works generally, but as a computer scientist, how would we formally explain the series of steps that it takes to calculate any given Fibonacci number in the sequence? Let's take a moment to work this out on paper. Computer science is more often a question of math and logic than it is working on a computer. And when you're first given a problem of this type to figure out, it often helps to do it on paper. So, how are we going to explain how to calculate Fibonacci numbers? How are we going to come up with the step-by-step process or the algorithm? I'm going to run through by hand myself just to kind of get some idea of how I might explain that. So the Fibonacci numbers start out at 1 and 1, at least historically. There's a more modern definition of the Fibonacci numbers that starts out at 0, but we're going to go with a classic approach here. So 1 plus 1 is 2, 2 plus 1 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 13, and 21, and it keeps on going. So I know how that works. I can easily do that, but how do I set up the procedure for that? How do I set up that process? Well, let me think a little bit more specifically about what I'm doing. If somebody asks me what the first number is here, put little lines into these. If somebody asks me what the first Fibonacci number is, that N1 there, I'm just going to tell them, oh, it's 1 by definition. And same thing for N2. If they ask me about the second Fibonacci number, I just have to tell them it's 1. It's defined as that. But for all the other numbers, for the third Fibonacci number, it's based on the sum of the previous two. And I suppose one way I could think about that then is if you ask me for the third number, I'm just going to say, well, we'll have N1 and N2 be those first numbers, and then I'll add those together to get you your Fibonacci number. If you ask me for a bigger one, if you ask me over here, I'm going to have to figure out what these are first, but then I have to start at the beginning every time, but then I'm going to have to say, well, what did I have before? What are the two values before this one here? And I could still use N1 and N2 to calculate that. I'd have to save whatever was in N2. Maybe I could save that in the variable N1, wipe out what was there before. And whatever was in Fibonacci before, or F before, I'll save that as N2. And then I can add N1 and N2 again. They have different numbers in them now. And that will be my new Fibonacci value. Or if they're asking me for the fifth one, then I would have to save whatever was in N2 in N1. You can see I'm going through the same process. I'd save whatever was in F from before as N2 and add those together again to get my new F. So depending on where we're going to go through the same process of saving the numbers that we used before, calculating a new Fibonacci, saving the numbers that we had before, calculating a new Fibonacci. I think that process could work, that idea of looping through and constantly shifting values into our same variables there. So what would the pseudocode look like for that? I'm not going to write it in Java or Python just yet. What would the pseudocode look like for that? I guess I could say, let's define the Fibonacci function, and I'll send in a value n, and then I'll try and figure out, if n is 5, I'll try and figure out, well, is that the value 5? What is that? If n is 6, the sixth Fibonacci number, is that the value 8? And then I'll send that back as the answer. So this process I just went through, I need to define that as my pseudocode here. So if n comes in, and if n is 1, then I already know what the answer is. I'm just going to say if n equals 1, then return the result, or return the answer, 1. That's easy. And if n is 2, if they try and ask for the second Fibonacci number, well, that's also pretty easy. I'm just going to return the value there, which is 1. That's the second Fibonacci number. But if they ask for 3 or more, if n gets to be greater than or equal to 3, if I haven't returned one of these things, it's going to be a little bit more complicated. So what I'm going to do is just what I did here. I'm going to save the value 1 in a variable called n1. Put a little storage sign there that means store the value 1 in the variable n1. And I'll do the same thing with n2, store the value of 1 in n2. And then let's run through, and I'll set up a little counter here, and I'll have a counter that runs, counter from, I guess we're going for all the values 3, from 3 all the way up to n, whatever their n is. And as we run through this loop repeatedly, each time, well, what did I do here? I calculated f as the sum of the previous two. So f is going to be equal to n1 plus n2. And although I might be ready to send it back in preparation for additional calculations if I have to, I'm going to save n2 into the variable n1. So n1 is going to get whatever was in n2. And n2 is going to get this Fibonacci value, this f, that I just calculated. So I'll save those for future calculations if necessary. And by the time I've gone all the way through this loop then, I'll return whatever value has been stored in that Fibonacci variable, in that f, and that'll be my answer. So that's my little function. I think it's going to work. I mean, it makes sense as I've drawn it here. But I'm going to go ahead and run through maybe with the value 8, just to double check and make sure. If I try to get the sixth Fibonacci number, will I get an 8, a value of 8? So I'm going to run through by hand just to make sure this is working. And then we'll see if we can write some code. We should also look at probably some other algorithms for this. So yeah, so here we are. I think I'm all set. Let me send in, I'll call Fibonacci, and we're going to try and get the sixth value there. Well, so what happens if I call Fibonacci with a value of 6, with n equal to 6? I'll just write some variable locations here, some memory locations. N is going to have an initial value of 6. And, well, let me follow the algorithm then. Is n equal to 1? It is not. Is n equal to 2? It is not. Is n greater than or equal to 3? It is. I'm trying to get to the sixth Fibonacci number. So I'm going to store n1, store in n1 a value of 1. And this may be intuitive to you if you've done computer programming before. For people who are still learning about this, it's very helpful to go through these processes by hand. N2, that's going to have an initial value of 1. And then I've got a counter running from 3 all the way up to n. So my counter is going to start at 3, I guess. And there are other ways you could do this, but this is the way I chose to do it. And then I'm going to be calculating an f value here. I'm going to set that off to the side because that f value, that Fibonacci value, is the one I'm really interested in. And so, since my n value here, my counter hasn't yet reached the n value of 6, I guess I'm going to run through and start doing these things. So f is going to be equal to n1 plus n2. F is going to get the value of n1 plus n2. That's 1 plus 1, or 2. And if I was looking for the third Fibonacci number, that would be the answer, but I'm going to keep on going here. N1 is going to get the value that's stored in N2, so N2 is going to get put in there. There's a 1. F is going to get stored in N2, so here's F. I'm going to put that value in there as well. And again, if I was done counting, if my counter had gotten up to 6, I'd be done, and I would return this as my value. This would be the third Fibonacci number. It's a value 2, and that fits with what I figured out, but I still have to go through. So my counter now is going to go up to 4. F is going to equal n1, n2. I'm calculating now the fourth Fibonacci number. 1 plus 2, n1 plus n2, 1 plus 2, or 3. And again, I'm going to save those values. N1 is going to get whatever was stored in N2. N2 is going to get whatever was stored in the Fibonacci number there. And I'll go back up and check my counter value here. I haven't reached N yet, so my counter is going to go to 5. F is going to be equal to N1 plus N2. 2 plus 3 is 5. I'm calculating the fifth Fibonacci value there. I also have to transfer variables. N2 goes into N1. F goes into N2. And I'm going to go back up for the loop. Has my counter gotten to N yet? It hasn't, so we'll go one more time there. My counter, I'm doing the sixth one. I'm going to calculate the sixth Fibonacci value. F equals N1 plus N2. 3 plus 5 is 8. And I do go ahead and do these last two, even though they won't be used. 5 gets copied into there, oops, and 8 gets copied into here. And at this point then my counter is done. I've reached the end, so I'm going to return the value that's in F, which is 8, and that is the sixth Fibonacci number, according to my little list here. So that logic seems to be working for me. That's pretty good. I've used a loop here, and I've swapped around values in memory, and I've been able to calculate a Fibonacci value. If you've already studied the Fibonacci sequence, you know that there's another way to calculate Fibonacci values, another type of algorithm. And in this algorithm, you use a strategy called recursion. The topic of recursion is an entire study in itself, so we're not going to really fully develop that idea here. But here's the general process. If we could, and I'm going to define a new Fibonacci function here, I'll shorten it to fib there. If, as we saw in the last example, if we saw that the Fibonacci number for any index is just the sum of the previous two values, at least for most of it, then one way we could really easily solve that, or at least easily develop a solution, is just to say, you know, I'll get your answer for you. I'm just going to return, if you're looking for the nth value, that's just going to be the sum of the Fibonacci from 2 before that one plus the Fibonacci from 1 before that value. Fibonacci of 6 is going to be Fibonacci of 4 plus the Fibonacci of 5. This is going to take care of that process of going back and doing our previous answers there. I do have to have when you're using this strategy, this recursion, you have to have a base case. You have to make sure that you don't go on forever and ever. So we do have those base cases that were defined at the beginning. If n is equal to 1 or n is equal to 2, then you know that we'd return the value 1, because those were the first, 1 was the first and second value there. Otherwise, if it's not 1 or 2, we're going to go through this process and develop that sum. And this is a really interesting, it's a fascinating process to watch. A little bit crazy, a little bit Alice in Wonderland down the rabbit hole. But let's see if we can trace through and figure out then how we would calculate the Fibonacci value of 6. How would we get that? Well, what we do is I've got my n value here, 6. Let's go and jump in. We'll just go in here and say, is n equal to 1 or n equal to 2? It's not. So I'm going to return then a value of 6 minus 2, n minus 2, or Fibonacci value of 4, plus the Fibonacci value of n minus 1, 6 minus 1, 5. So the Fibonacci value for 6, the 6th Fibonacci number, is just equal to the sum of the previous two, the 4th and the 5th. Okay, well, how do I get the value of the 4th one? That's going to be equal to the, what we're going to do is we're going to call this function. It's going to actually go back up there and call Fibonacci 4, and that's going to be equal to the sum of 2 before 4, or 2, and 1 before 4, or 3. And so as I go down here, I look at Fibonacci of 2. Do I know what the Fibonacci value of 2 is? If n is 1 or n is 2, I'm going to return 1. I already know that one. That's my base case. So I'm going to return a value of 1. And the computer, in running through this code, is going to say, okay, fine, I got that 1. Let me go in and now double check this. What's Fibonacci of 3 going to be? Well, that's going to be fib of 2 before 3, or 1, plus Fibonacci of 1 before that, of 2. And Fibonacci of 1 I know is 1. And Fibonacci of 2 I know is 1. So these values, 1 plus 1, in returning, we'll sum those values. And this means this comes out to be 2. And 1 plus the 2 here comes out to be 3. And I'm doing really well. I just need to take that 3 and add it to the Fibonacci value of 5. Well, let me jump in there and figure out what's going on with the Fibonacci value of 5. That's going to be equal to index 5, 5 minus 2, or Fibonacci of 3, plus the Fibonacci value of 5 minus 1, or 4. This is really interesting because although I've already calculated Fibonacci of 4 over here and Fibonacci value of 3 here, when you do recursion like this, unless you do some pretty fancy stuff, I'm not going to know, the computer's not going to know the values that have been calculated over here separately. So we have to continue going down this rabbit hole of calculating fib 1 plus fib 2. And fortunately, those are pretty easy. That's 1 and 1. 1 and 1 is 2. So I'm going to add 2 to whatever Fibonacci 4 is. But now this gets, well, you know it gets painful. That we're going to do fib 4 equal to fib 2 plus fib 3. I'm running out of space here. Fib 2 is 1. Fib 3 is fib 1. 1 plus fib 2. I'm killing myself here. Here's a 1. Here's a 1. Here's a 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. The 5th Fibonacci number is 5. The 4th Fibonacci number is 3. And I add those 3 and 5 together to get a value of 8. I'm exhausted. But that's recursion. You go through, you have this function calling itself in a modified form over and over and over. And eventually, you get to the correct answer there. Again, this is a recursive function because the function calls itself with a modified form, and it has a base case that makes sure it doesn't go on forever and ever and ever. So we've got two strategies for calculating Fibonacci values, one of them based on the loop and one of them based on the recursion. I should mention here that computer scientists have a way of analyzing the efficiency of an algorithm. This efficiency measurement doesn't have to do with how quickly the algorithm works or even how quickly the program runs on the computer. The computer scientists' measure of efficiency is based on how well the program can deal with problems of increasing size. This efficiency is expressed in something called Big O notation, a really interesting subject that we'll have to wait to talk about until some other time. As somebody who does a bit of computer science and a little bit of computer programming, at some point I shift my role from thinking about the algorithm to actually implementing the algorithm on the computer. So we're going to take a look at a few programs here, 2 of them in Python and 2 in Java, and these programs are attempts to implement these Fibonacci algorithms, and then we'll see how they work. So first of all, let's take a look at a Fibonacci program written in Python, and we'll use the loop strategy for this one. So this is written in Python 3, and you can see what's happening. It looks pretty straightforward compared to what we wrote for our pseudocode before. I've got a Fibonacci function here that I'm defining, and if n is 1, we return 1. If n is 2, we return 1. And if it's anything else, then we go through that process of repeatedly calculating a new Fibonacci value going. And eventually, we return a Fibonacci value there. So let's take a look and see how this program runs when we actually use Python on it. So I know the Fibonacci value for 5. It should be a 5. That comes out. That's good. Let's run it again and try the 6th one. We know that that's 8. We worked that out. That's pretty good, and it seems like this, well, computers are fast, but it seems like it's calculating this pretty quickly. If I calculate the Fibonacci value for 40, that comes up with an answer. I don't know for sure if that's the correct answer, but the logic in my program seems pretty good. And Python's really good about calculating with large numbers. It doesn't require any special facility to do that. I'll do 100,000 for the Fibonacci value. I want to get the 100,000th Fibonacci value. And oh my goodness, yeah, a lot of numbers there. And again, the logic in the algorithm is correct, so I think Python's probably doing a pretty good job with this. That's awesome. I want to try and look then at a Fibonacci program that uses recursion in Python. So here's what that one looks like. You can see it's a much more efficient program, at least in terms of writing it, because I'm using recursion. The way I've set it up here is I say, well, if n is the value 1 or 2, I'm just going to return 1. Otherwise, I'll do that recursive thing, the n minus 1 and the n minus 2. Very, very efficient in terms of the space here. And let's see how it runs when we actually run that in Python. So we're doing the recursion version, and I know what the answer is for 5. Oops, there's 5. That worked out okay. What about the 6th value? That's an 8. That's pretty good. Let's try the 10th value. It seems to be working very well. I'm going to jump up to 40 here, and well, this is taking a really, really, really long time. And you may recall that when I was actually trying to calculate that Fibonacci value using recursion, I ended up duplicating a bunch of the work I was doing. I ended up recalculating a bunch of values. And the fact that this program is taking such a long time to run is a reflection of that. It's not that there's anything wrong with the algorithm. It's a great algorithm. And there's nothing wrong with the program. The program works just as it should. It's just that this particular algorithm takes more time. It got the answer there. Is that the same answer that I got with the loop when I was doing the loop one? Here, let's try the loop one and double check. We were trying to figure out the value for 40. Oh, that loop is so quick compared to the recursion. Still, there are some advantages to recursion. Nothing wrong with recursion. It's just that in some cases, it's not as efficient. Well, I want to do the same thing with Java programs. Let's take a look at calculating Fibonacci sequences in Java here. I'll take a look at this. Here's a program I wrote just using a regular Java class here. Fibonacci loop is the class, and I'm doing pretty much the same thing that I did before. I set up a little static method here, a function if you like, to calculate a Fibonacci value based on the index n there. And if n is 1, I'm going to return 1. If n is 2, I'm going to return 1. And same process, same steps here that I used in the Python program. And then I've just got a little main program down here that calls it and prints out the answer. So let's try running that and seeing what happens in Java. Hopefully it'll be just fine. The 5th value I know is 5. Oh, that's awesome. The sixth value I know is 8. Good, we've done those. What about the 10th value? Is that pretty good? That's not too bad. What about the 100th value? Uh-oh, this isn't right. I shouldn't be getting a negative value for adding things together. And I actually do know why this is giving me a problem here. The challenge is I'm starting to calculate, when you're doing Fibonacci's, you're starting to calculate some pretty big numbers. And I've been trying to store all these values into an integer variable. And the integer variable, although it can store some pretty big numbers, it doesn't go on forever. So fortunately, Java has the ability to, it has a class called the big integer class that we can use. So let's take a look and see what that looks like, because I do have a version of that we can see. And using the big integer class, you have to import this library, and you're setting this up. And it's not quite as intuitive or quite as convenient as doing integers, regular integers. If you want to use big integers, you have to use these methods, value of, to manipulate them. And it's not quite as efficient as an integer, but again, we have the ability to work with very large values. And if it's not quite as efficient as working with just straight integers, it has the benefit of being able to work with, as the name would suggest, really big integers. So let's see what it looks like if I do a calculation with that. It's still going to get the small values for us just fine. And if I run it now and try and get the 100th value, that's starting to look like a more reasonable value. I can compare that with the Python value and see if that's what we got for our 100th value. Oh yeah, those are working just fine. And so Java, of course, let's go with the 100,000th value. Oh, very quick, very quick. It's getting very large numbers very, very quickly. So it's actually pretty good there. So we've seen that the fields of computer science and computer programming are both related to computing things, but they also have some important differences. Computer science is logical and mathematical in nature and mostly concerned with figuring out how to compute things using algorithms. Computer programming, on the other hand, is based on knowing a specific language and coding an algorithm so that it works in that language. Every program, whether it's managing information or making calculations or drawing or calculating the position and velocity of a character in a video game, every program makes use of algorithms. And whether you're a computer scientist or a computer programmer, working with algorithms is fundamental to what we do. This is Richard White, and this has been a brief presentation on computer science versus computer programming, algorithms, and the Fibonacci sequence. Thanks for watching.